A data center is a large building full of racks of computers with hard drives, all connected internally with fiber or copper, and connected to routers that have fiber connections to other data centers and internet exchange buildings on the outside. Here are some pictures of the exterior of various data centers. Some of the early designs attempted to incorporate aesthetics, solar panels, and windmills. More recent designs are just big box, nondescript designs. The China Telecom Inner Mongolia Information Park campus was, at time of writing, the largest data center in the world, or at least it was planned to be, with a purported capacity of 100,000 racks when fully built in 1.1 million square feet across 6 data halls located in a campus of 11 million square feet. The China Mobile Hohhot data center nearby claims it'll support 40,000 racks when fully built. Here's an aerial photograph of the campus from 2025 and presumably an artist's conception of what it will look like when fully built out. The United States government built a 100,000 square foot data center known as the Bumble Hive, or more formally, the Intelligence Community Comprehensive National Cybersecurity Initiative Data Center, or the Utah Data Center, which seemed huge at the time. The reason that they built it in Utah was because there are a lot of Mormons in Utah, and they figured that Mormons are decent, upright, patriotic people, so that's a good place to put this extremely sensitive national security asset and all of the employees who work there. Other people might think that the reason why they put it there is because of its close proximity to all of the great ski resorts in the Park City area. This is where a record, if not actual copies of every file you have ever downloaded over the internet are stored for future investigations, as well as supercomputers for cracking encryption keys and the software that manages it all. At time of writing, this file was downloaded to you from one of the QTS data centers in Atlanta, coming in at 800,000 square feet of data hall space. Here are some pictures of the interior of data centers, rows of racks of shelves holding computers. Data centers are being built everywhere, but are concentrated in specific areas for reasons of proximity to big users like the United States government, proximity to other data centers and to internet exchange buildings to facilitate interconnection, areas where there's abundant fiber infrastructure, areas where land is inexpensive, where cooling is less expensive, and where power is less expensive. One of the first areas with a concentration of data centers was Grant County in Washington State. That's over the mountains from the Pacific Ocean to the west of Spokane. Its territory includes part of the Columbia River, on which the Grant County Public Utility District built 2 hydroelectric dams, whose electricity is sold at advantageous rates to data center operators. More recently, Ashburn, Virginia came to have a high concentration of data centers in an area known as Data Center Alley. Here are some maps showing the location of data centers in Ashburn and Chantilly to the south, though of course people in France pronounce that Chantilly, not Chantilly. Companies like Amazon Web Services and Microsoft have their own private data centers and use computers and software they design to best meet their needs. In a commercial multi-tenant data center, companies can rent floor space that comes with power and cooling and install racks of computers. But actually it's the other way around. Companies can rent power that comes with floor space and cooling and install racks of computers. Co-location is a term that pops up in discussion of multi-tenant data centers. Co-location means physically situating equipment beside another company's equipment. This is used in data centers to mean several things. The idea of tenants locating racks in a data center in proximity to and connected to other tenants' racks, and the idea of sharing a third party's very high bandwidth internet connection to the data center. One of the biggest challenges in data centers is getting rid of excess heat. The computers, with their processors and RAM, generate enormous amounts of heat that must be transferred out of the data center to avoid catastrophic temperatures inside the data center building. Water is a popular medium to carry heat from inside to outside. Here are some pictures of the water-based cooling systems at Google data centers, with huge pumps and the inflow and outflow pipes painted the Google colors. This data center in France uses cooling towers like those for nuclear reactors to get rid of heat in the form of steam. It is, of course, advantageous to locate a data center in a naturally cool geographic area, one of the reasons for the Chinese data centers in Mongolia. At a Google data center in Scandinavia, not only is cold water freely available, it's also possible to do ice fishing during lunch break. Fiber connections to internet exchanges are required to connect the data center to the internet. Large tenants will have their own redundant connections, and a service offering of the data center or a third party can be capacity on a shared physical fiber. For extreme requirements, for example, a specification of a maximum of 20 milliseconds delay between data centers to implement seamless fault tolerance or high-frequency trading, the proximity of the data center and the length of fiber required to connect it is a factor. For less extreme requirements, the length of fiber to the data center is moot, allowing the construction of data centers in remote locations where electricity and cooling are economical. Success in a multi-tenant data center business requires, of course, customers. The ideal customers would be the likes of Netflix, Bank of America, and Cisco, stable customers with deep pockets who will sign long leases. Leases with startups, small organizations, and resellers would be more of a business risk. Power is going to become the biggest challenge, not just for the data center operator, but for the residential and non-data center business customers of the power utility company where the data centers are being built. To provide power to new data centers, the utility must build new infrastructure. This includes purchasing and installing high-voltage transmission lines and the pylons to hold them in the air, transformers, substations, and new generating capacity. In the regulatory framework of many power utilities, the cost of the infrastructure build is distributed to all customers of the utility, not just to the data centers that are the reason for the new infrastructure. This is causing the electricity bills of all users to spike. Here's one chart from the U.S. Department of Energy showing the revenue increase per state from 2024 to 2025, which they use as a proxy for the price of electricity increase. Now compare this to another chart from the DOE showing the increase in retail sales, i.e. residential consumption over the same period, which is pretty much flat. It's immediately obvious that electricity costs for homeowners and non-data center businesses have radically increased in just that 1 year. In some cases, over 20% in 1 year. And this is just the beginning. According to the Department of Energy, the average U.S. household uses about 30 kilowatt hours per day. So the average continuous load for a single-family home is about 1.25 kilowatts. However, that's the average over day and night and over all of the customers. The peak consumption per customer is around 15 kilowatts. But since different homes draw peak amounts of power at different times, the planning value of peak consumption for a neighborhood is usually 3 kilowatts per customer. Factoring in EV charging and bigger houses with central air and electric heating going forward, let's call it 4 kilowatts average peak per residence. Racks in data centers housing traditional computers made of, for example, Intel CPUs, RAM, and solid-state hard drives, like those found in PCs, require 5 to 10 kilowatts of power per rack. Racks in data centers housing AI computing, made of, for example, Nvidia chips, are currently headed towards a requirement of 100 kilowatts of power per rack. So that's the generating capacity needed to power at least 25 homes per rack. And with anything AI, it must always be kept in mind that this is just the beginning. Going forward, the numbers will be much higher. Nvidia has announced rack products using 600 kilowatts of power, the one pictured, then 1,000 kilowatts or a megawatt per rack for availability before 2030. That's the generating capacity required to power 250 homes, at least, per rack. That would mean, in theory, that the China Telecom data center cluster in Mongolia, if converted to AI racks at 1 megawatt per rack in the future, would use 100,000 megawatts or 100 gigawatts, which is the peak generating capacity required to power at least 25 million homes, more than all of the homes in the Pearl River Delta that's pictured. The climate environmentalists can only hope that they don't burn coal to produce that electricity.